Good morning, everyone. Good afternoon or good evening, wherever you are around the world. Big ML asked me to participate in this conference as a speaker to explain our case of usage in Indorama. And it is a pleasure for me to contribute with it to this event. Congratulations to Big ML for adapting so fast this event to these circumstances so special that we are living today. Well, having said that, let's go through. As shown in the title, we have applied machine learning for quality optimization. And what it means, quality optimization for us, this encloses a target to comply with product specification at the same time that costs to do it is minimized. This is a challenging issue that requires analyzing multivariable effects in it, as we will see. And then let's start. We will take a view to the background of the company first. I will explain about the process where we have applied the methodology, and we will see what is the methodology applied of BigML. We will take a look as well to some example of the results obtained, and at the end, I will show a summary of what we have seen. We will talk about Indorama Ventures and PET, especially that is one of the most important products that we manufacture. And integrated in it, it is the carboxylic acid process as raw material for PET production. You can see here the chemical formula of the polymer. Okay. PET, we are a leading manufacturer in Indorama of the PET. We offer product in different grades, including hot fill, high and low intrinsic viscosity, quick heat, and general grade, and much more. And what you can see here are the pellets that are melted to produce at the end the containers for bottles, for foods, and for fibers as well. And at the end, it's product that can be recycled. We have a big compromise with environmental protection, and aligned with this target, we have the strategy to recycle more and more PET. At the end is used for new bottles, but with an important composition of recycled PET. These are the locations of our operating sites, with more than 102 operating sites in 31 countries around the world. The products that we produce, the PET, is used for many different usages, as you can see here, for drinking bottles, for containers of many kinds, fruit containers, microwavable trays, synthetic clothes. It's used as well in construction for wall insulations and as well for synthetic carpets. Let's drive now the presentation to the process where it has been used, BigML. And it is specifically this part of the process that is integrated between the xylene that is coming from the refineries, and finally for the production process specifically of PET. This is the carboxylic acid process that we will look through a simplified block diagram in the slides coming now. Where we want to optimize, it is at this step in order to reduce the production cost while keeping the quality parameters. This is the block diagram of this carboxylic acid process, where you can see here from the left to the right, there is some steps like a feed preparation of chemicals. Here it is mixed, the raw materials that are going to be used to be react in a reaction. In this reaction, these chemicals are combined with air coming from atmosphere, used with a compressor to mix it at a certain pressure and temperature conditions in the reaction. Carboxylic acid is produced here and is crystallized in the following stage, filtrated under vacuum filtration, then dried and stored in a silo where quality is analyzed. This process integrates recycles internally that have its effect in the control of this quality as part of it. The quality is analyzed here and is a parameter to be combined with the production cost in a target that we will see. The production cost at the end means saving chemicals used in this part of the process. Like it is a solvent of acetic acid, the main raw material that xylene, and catalyst as part of the reaction. Something that might seem simple in this sketch, it has, however, many variables involved behind. There are catalyst effects, and there are several catalysts, every one with effects in reaction, independently or associated to each other. There are silane concentration effects. There are recycled intermediate effects. There is an effect of air for the oxidation. There are temperatures effects. There are pressures effects. There is residence time in reaction, in crystallization also, as well in filtration conditions, what makes quite complex to find the optimum. Then, the target is to obtain a model for optimization for process parameters, focus on carboxylic acid quality while minimizing raw material and solvent losses. Then we use some reaction parameters that can predict the raw material consumption. And these parameters are combined with quality to look for optimum conditions. This is a view of the methodology applied with BigML. So we provided a source of data to BigML to create a data set. This data set needed to be clean, needed to be filtered in order to create a future engineering and a future selection that would be used to obtain some unsupervised models and start having anomaly detections, association discoveries, and clusters identifications. With the exploration of data, with the weight of every variable in this exploration of data, were identified the prevalence of those variables that needed to be included in the final data set to be put in the models and optimizations of the model using OptimML at the end to have results that we will see how they were obtained and with what kind of accuracy, recall, and precision. This is an image of the clean and filtering done. We used a data set of 2.5 years that involved with all the variables used, like approximately 6 million data used. And this is the view of the filtration that needed to be done. So it can be seen that there are periods of time in these 2.5 years where there are results that are not normal, that would create a lot of noise in the analysis and needed to be filtered. This square, for example, delimits one of those periods. These small peaks that can be seen here as well identified some others. So all this filtration was very useful in order to progress with the analysis. Additionally, this table shows what is the relationship as part of the association that the variables might have between each other. In this table is reflected the Pearson coefficients that show this relationship. So the greener values are the ones showing the biggest relationship, and less going through the bright blue and light blue up to the white, where it can be seen that there is no relationship. All these are tools that helps to identify what is the amount of the impact that there is between the connectivity of the variables to be considered for the model. The relevance of variables is another very helpful tool that allows as well to see what are those variables that should be selected as the most important ones for the model to be analyzed. This is part of the features selected during the stage of the engineering, future engineering. What it can be seen here is a list of variables of all those multivariables that I mentioned during the process presentation that can have an effect in the process. So in the columns, we can see that there are different features combining all of them or only part of them, depending on the weight detected as shown before. This is a way to simplify the exercise to avoid irrelevant noise that could complicate the analysis without need of it. Here we can see variables that are the throughput of the process, the concentration of the catalyst, water, oxygen, the ratio of air compared to the feed to the reactors, intensity of agitation, leveling reaction that at the end has impact in the residence time of reaction and its efficiency. So all these kind are the ones who were evaluated in this sense. Having passed to all these stages of the analysis, we made an optimization. We ran the model and made an optimal, and it was obtained more than 90 models with the optimal I've shown here with different kinds of accuracy, recall, and precision. And we selected the ones that we considered that might provide the results that could be more in agreement with what we have observed in the process. This slide shows how these models reflect the weight of every variable in the model executed. So it is surprising that in some cases it is found that are identified variables that have a weight that someone knowing the process after many years would not expect. So this is one of the interesting things of this machine learning is that we open completely our eyes to new discoveries that human might not find by himself alone. This is the first example of result that was found with one of the models, and this is the evaluation. So let's explain about the coding here. Green values in the lines show reality. Desired values here would be 146 totally of all the amount of data predicted, and unwished it would be 3,591. So out of these desired values in green, the model predicted 46 and considered that were unwished 100 out of the 146 that were really desired. And again, considering that desired, it would mean good quality with minimum production cost. And about the unwished, the model would predict 3,585 out of 300 and 591 good results. And however, it would assign as wish 6 out of these 300 and 900, 3,500 that were unwished. So what does mean about that this model? First, what we saw is that was very unbalanced because there were very few results positive and a big amount of results that were unwished. So at the end, even though it was obtaining a very good accuracy of results and good precision, the recall was poor. Then we went through further analysis, modifying the data sets to more granulated values, making shorter period of times and much more granulated, changing the average of the data provided, and for a shorter period of time. And in this case, we saw that we could improve that recall to an 89% compared to the 30 something that we had before, and keeping very good accuracy and keeping very good precision. We evaluated the model. As you can see, there are different types. The decision tree, there is a PDP, and there is a sunburst that is a top view of this decision tree. We prefer to use the PDP in our case in order to evaluate the percentage of successfulness that we might have by changing the variables, as I will explain now. This is a view of the sunburst that shows for a very few results of positive what are the conditions that could lead to a desired value. But again, we prefer to go to a PDP analysis in the way that I will explain. We focus on our analysis in several variables and establish different levels for everyone. Let's talk about variable 1. We establish a level 1, 2, and 3 for it. And for every variable, we choose a variable 2 with 8 levels of variation for this level, variable 2 in every case. And for every level of variable 2, we establish a variable 3 and a variable 4 that are the ones that we played with in order to move through the PDP to establish the percentage of successfulness that we might have by changing them. In every PDP, we're fixed all the rest of variables. And as I said, this is a multivariable analysis, so many ones were fixed in order to establish the desired value for the quality and production optimum cost. So if we go to variable one, level one, then we played with 8 levels of variable 2, as you can see here, level 8, 7, 6, 5, 4, 3, 2, 1, creating different PDPs. And in every PDP, we moved variable 3 and 4 in this surface in order to see where we might get the most successful result in quality and production cost. What are the color coding here? The color coding here means the more orange color is the higher percentage of success. The bluish is the less. In some cases, the darker areas means that there might not be sufficient data in the data set to identify this could be an area of interest or not. But whenever there are data sufficient in these orange or blue colors, this point of optimum conditions could be identified. So what we could see with this is that moving variable 1 to level 1, 2, or 3, there were certain conditions where we could see where we could get the maximum probability of success with quality and production cost. So level 3, we can see here that there was a blue color, so not successful areas, and the orange ones could provide values of 85, 89%, 90, 95 in some cases, but where we could see specifically the biggest area of good results, it could be identified thanks to the optimal in the variable 1 and level 2 for variable 1 and level 8 for variable 2 for this area of variable 4 and variable 3. This has been very helpful for us in order to confirm result of the process by putting this variable in this area of operation. Then in summary, model obtained provides statistically very good results and compare with real effects seen in process. It seems to be adequate to predict probability of success in quality and efficiency of reaction. This first exercise, made in Indorama Ventures Química, opens the door for further investigation by adding more and more data sets, exploring new ranges of operation for variables, and letting the application to learn and recommend even higher levels of optimization. Thank you very much.